Hello, everybody. Welcome to part one of our three-part applied remote sensing training, satellite data for air quality, environmental justice, and equity applications. My name is Melanie Follett-Cook. I am a research scientist at NASA Goddard Space Flight Center, and I will be hosting today's training. You can see from this slide that I'll be joined by a variety of exciting speakers for today's session focusing on the use of satellite data in environmental justice applications. Before we begin our training, I just want to give a brief introduction to the RSET program. NASA's Applied Remote Sensing Training, or RSET program, is part of the NASA Earth Science Applied Science Capacity Building Program. We provide cost-free training on the basics of satellite observations, data processing, analysis methods, and ready-to-use web tools in the 6 thematic areas shown here: disasters, agriculture, ecological conservation, water resources, climate and resilience, and health and air quality. Our trainings are offered both online and in person, but the majority of our trainings are online. All of our training materials, recordings, Q&A transcripts, are available on our website, so you can register and participate live as you are today, or you can review our past trainings in your own time. We also offer a self-paced training on the fundamentals of remote sensing. Our trainings are offered at no cost and usually include a bilingual option, whether that's translated materials or the training itself is delivered in Spanish. And we only include publicly available open source software and data. Our trainings are offered at a variety of levels, from introductory to advanced, to allow you to learn remote sensing based on your level of experience and need. If you'd like to know more, please visit our website. From there, you can find information about and register for upcoming trainings, view recordings, review material from past trainings. You can also sign up for our listserv to be notified about upcoming training opportunities. So to begin today's part, I'll provide an overview of our whole training before we begin part one. Many populations around the world face environmental challenges, including extreme heat, flooding, drought, poor air and water quality, and more. Minoritized and marginalized communities, particularly in the poorest and most vulnerable areas, often experience disproportionate exposure to a range of these environmental hazards. Satellite remote sensing observations, with their unique capability to collect large amounts of information over space and time, can support environmental and climate justice efforts by supplementing on-the-ground efforts to investigate such disparities in risk exposure from global to local scales. By the end of this training, participants will be able to describe at a high level how satellite data have been combined with socioeconomic information to investigate environmental justice issues such as heat exposure or access to green space. Identify remote sensing data products which are most relevant to assessing environmental justice related air quality and pollutant exposure. Articulate the benefits and limitations of using remote sensing data to assess environmental justice concerns related to air quality. Import relevant air quality datasets into EJ-Screen and use EJ-Screen to investigate and compare air quality with environmental and demographic datasets. Pair appropriate satellite datasets for environmental indicators, air quality specifically, with demographic information using Python. We'll be recapping some basic concepts from this training where they're relevant, but we strongly recommend taking this training first. Our Fundamentals of Remote Sensing training is a self-paced online training that can be found on our website. Here, we can see an outline of the training series. It will take place over 3 weeks and consist of 3 parts, each 1.5 hours, plus a 30-minute Q&A. All presentation slides, recordings, and Q&A transcripts will be available on our training page. There will be 1 homework assignment, which will open on the date of the final part on September 6th. It will remain open for 2 weeks and close on September 20th. A certificate of completion will be awarded to those who attend all live sessions and complete the homework assignment before the given due date. Part 1 of this training series will give a broad overview of the use of satellite data across a wide range of environmental justice applications. To support this broad view, we've invited several guest trainers to present on their work related to using satellite data to investigate environmental justice issues. Susan Annenberg and Xiao Shen, professors at George Washington University and the University of Texas, respectively, are the leads of the NASA Health and Air Quality Applied Science team on satellite data for environmental justice. Tanya Kreutzer-Syed and Ufama Ovemida are PhD students at UMBC and MIT, and Daniel Wood is a professor at MIT. Daniel Carrion is a professor at Yale. These guest trainers will be presenting throughout the training today, giving overviews of their work related to using satellite data to investigate different environmental justice issues in the US and around the world. You'll also hear from me, RSET trainer Melanie Follett-Cook, as well as Shobhana Gupta, Associate Program Manager of NASA's Equity and Environmental Justice Program. By the end of Part 1, you'll be able to describe, at least in a general way, how satellite data have been combined with socioeconomic information to investigate environmental justice issues, including heat exposure, light exposure, access to green space, and air pollution exposure, to name a few. You'll also be able to describe the benefits and the limitations that satellite remote sensing data have with respect to their application to investigating environmental justice issues. Before we get started, I just want to remind everyone that if you have questions, please type them into the question box of GoToWebinar. We'll be collecting these questions and answering them at the end of today's training. We will also be compiling these questions and answers into a Q&A document, which will be posted to the training website in about 1 week. Any questions we do not get a chance to answer live will still be recorded along with our answers in this document. So to start this session, we need to understand, what do we mean when we use the term environmental justice? According to the US EPA, environmental justice, or EJ for short, is the fair treatment and meaningful involvement of all peoples, regardless of race, color, national origin, or income, with respect to the development, implementation, and enforcement of environmental laws, regulations, and policies. Within this definition, fair treatment means that no group of people should bear a disproportionate share of the negative environmental consequences resulting from human activities, including both in the public and private sectors. Meaningful involvement means that people should have an opportunity to participate in decisions that may affect their environment and health, that the contributions of the public should influence the decisions of regulatory agencies and policymakers, that the concerns of communities collectively should be considered in decision-making, and that decision makers need to actively seek out affected individuals and communities and facilitate their involvement in environmental decision-making. While environmental justice is our goal, unfortunately, environmental injustice is often the current reality, with different groups and communities being disproportionately affected by different environmental risks and hazards. When speaking about this, we use the term underserved communities to refer to populations sharing particular characteristics, including social and economic characteristics, but also shared geographical communities, which have been systematically denied the full opportunity to participate in social, economic, and political activities, as is required for their meaningful involvement in environmental decision-making. A related concept, environmental justice, or EJ, communities, refers to geographic locations with a significant representation of persons of color, low-income persons, Indigenous persons or members of tribal nations, and other groups who experience or are at risk of experiencing more adverse human health and environmental outcomes. So while an underserved community is a bit more of a general definition, EJ communities are specifically geographic areas where these underserved communities might be found and are particularly at risk for negative environmental and health outcomes. NASA's main role here, which has been assigned to the Earth Science Division and NASA in particular, is to ensure that the investments made by the American people in NASA's satellites and all the infrastructure and science that go along with them are used to equitably benefit everyone across the US and to help them make more informed decisions about the challenges they face in their communities. Practically, this means making NASA's satellite and remote sensing data of the Earth, or RSD, free and publicly available and accessible. In addition to simply providing the data, NASA has an obligation to provide training and capacity building, like the RSAT training you're attending now, to help people understand how to interpret and use different types of remote sensing data in the most effective way. Finally, NASA also funds fundamental research to develop new ways to use current and potential future remote sensing data to investigate and address many kinds of societal challenges, including challenges and barriers to achieving environmental justice. At NASA, these tasks are mainly carried out through our Applied Sciences program. The Applied Sciences program helps people across the world use NASA data to solve their biggest problems, including environmental injustice. One way is to provide direct funding to support research and decision-making about problems related to health and the environment. But in addition to funding opportunities, the Applied Science program includes NASA's capacity building efforts, which are RSET, which provides free public training, such as the one you're attending right now, Develop, which supports small research teams on short-term feasibility studies for new applications of NASA Earth science data, and Servir, an international program in partnership with USAID, which provides international decision makers with the tools and training they need to use Earth science data. The capacity building program also includes an umbrella area called Community Action, which includes elements for Indigenous peoples, prizes and challenges, and equity and environmental justice, which we'll hear about more in just a minute. Another effort supported by the Applied Sciences program is the Health and Air Quality Applied Sciences Team, or HACAST, which partners researchers with public stakeholders to use NASA satellite data to solve public health and air quality problems. HACAST includes its regular team members as well as shorter-term partnerships organized as Tiger teams and rapid response teams. One of these HACAST Tiger teams is the Satellite Data for Environmental Justice, or SD4EJ Tiger team, led by Susan Annenberg and Xiao Qian, two of our trainers today. The goal of this team is to integrate satellite data into existing mapping and screening tools, which support environmental justice applications. To do this, the team includes many partners in federal, state, university, and nonprofit organizations. And you'll see several examples of how satellite data have been integrated into these organizations' tools in this training. And now I'll pass it to Shobana Gupta, who will tell us about NASA's Equity and Environmental Justice Program.
Thank you, Melanie. Hello, everyone. My name is Shobana Gupta, and I am one of the Associate Program Managers of NASA's Equity and Environmental Justice Program, or EEJ. Our program aims to empower communities across the US and around the globe to use Earth data and make informed decisions about issues affecting them, and cultivate new partnerships to support community outreach, training, and the development and application of Earth-based insights. EEJ invests in community understanding and use of Earth observations through many existing NASA's programs. These programs include funding and capacity development opportunities, like research opportunities in space and Earth sciences, or ROSES, future investigators in Earth and space science and technology, or FINEST, advanced information systems technology, or AIST, Develop, Indigenous Peoples Capacity Building Initiative, and Prizes and Challenges. You can learn more about our program by visiting our program page in the NASA Applied Sciences website, appliedsciences.nasa.gov. Additionally, EEJ is organizing knowledge sharing opportunities within and outside NASA for EJ communities, researchers, and other stakeholders to discuss their work, challenges, and goals with one another. I now want to share more about projects from our primary funding opportunity, ROSE's A.49. This solicitation offered opportunities for research to advance progress on equity and environmental justice domestically through, firstly, better understanding of community and stakeholder needs, including issues faced by EJ communities, their engagement preferences, and areas for EEJ to provide support. And secondly, through increased integration of appropriate Earth science, geospatial, and socioeconomic information in their work. 39 projects were selected to receive a total funding of $6.9 million for up to 3 years and cover a range of environmental justice topics, including wildfires, flooding, and urban development. You will have the opportunity to hear from two of our investigators, Daniel Carrion and Danielle Wood, later in this training. The A.49 projects are classified into 3 elements: landscape analyses to understand the broader EEJ community context to inform actionable next steps, community-based feasibility projects that apply earth science information to demonstrate the feasibility of the approach with suggested expansion opportunities, and finally, data integration projects that combine earth science information and socioeconomic information into GIS-enabled tools to serve community decisions and actions. EEJ plans to release the next funding opportunity, ROSE's A.47, later this year. For more information, please check the NASA Research Opportunities website, NSPIRES, where you can subscribe to receive NASA solicitation announcements. Thank you.
Thank you, Shobana. Now, to give us an overview of how satellite data have been used to investigate various environmental justice issues, I'd like to hand us over to Tanya Kreutzer-Sayed and Ufoma Ovemida.
Hello, I'm Tanya Kreutzer-Sayed, a health policy doctoral student at the University of Maryland, Baltimore County.
And I'm Ufoma Ovemida, a PhD student at the Massachusetts Institute of Technology in the Department of Aeronautics and Astronautics.
On behalf of an amazing team of 12 authors, I'll present our research which demonstrates how satellite data can be combined with diverse data sets to explore environmental justice issues. Earth observations from satellites in space are important because their abilities can reduce environmental justice research gaps which exist from using traditional or ground-based measurements and monitoring methods. We conducted a satellite data for environmental justice scoping review to explore how researchers use satellite data to reveal patterns of inequities facing populations in the United States. After I provide an overview and introduce satellite data for environmental epidemiology, my colleague Ufoma will dive deeper into satellite data. We'll conclude with insights on how the studies we found contribute to environmental justice and public health efforts at policy, agency, and community levels. Let's take a look at our aims, methods, and results. We aim to first explore trends in study types, topics, geographic scope, and satellite data sets used to research environmental justice. Second, to synthesize findings from studies using satellite data to characterize population disparities across different environmental topics. And third, to capture how satellite data is relevant to policy and real-world impact. We followed a 5-step review framework and the PRISMA reporting method. Our study's inclusion criteria were first to be US-based peer-reviewed studies published between 2000 and 2022. Second, that authors use direct or indirect satellite data as an independent variable to observe and measure an environmental condition. And third, that authors reported on some differential exposure, vulnerability, or other environmental condition that was observed using satellite data which could also cause population disparities. We documented all data sets used and if and how researchers related their evidence to health, policy, urban planning, or community efforts. Take a look at this slide's example of environmental impact categories. Which do you think was the most researched category of the studies we reviewed? Pat yourself on the back if you guessed air pollution. Our review resulted in 81 included studies. Most of the authors leveraged satellite data for air pollution research. The green space and temperature studies were represented at approximately half of the proportion of the air pollution studies. Other environmental hazards we found were flooding, gas flaring, mountaintop coal mining, and light pollution. 11 studies actually concurrently investigated multiple impacts which could increase an individual's vulnerability and further harm their health. Take a look at this bar graph, which shows the study's environmental categories in years published. This graph demonstrates that more than half of the studies we found were published between 2020 and 2022. One reason for this may be the increasing availability of satellite-derived high-resolution data sets, which enable new environmental justice research applications. This slide shows examples of social categories and social data sets, which researchers used in combination with satellite data to explore differences. Race, ethnicity, income, and Medicaid eligibility status were more commonly used than redlining and subsidized housing. Popular data sets employed included the American Community Survey, the Centers for Medicare and Medicaid Services, and the Area Deprivation Index. We broadly defined environmental epidemiology as the study of the relationship between environmental exposures and morbidity or mortality. We closely examined studies in which authors combined satellite data not only with socioeconomic and demographic data, but also with individual or collective health or hospital administrative data to identify areas and populations with higher risks of exposure and vulnerability. The study we found by Wei et al. Is an example of a population study showing adverse health effects from environmental exposures to environmental hazards. They combined a daily, multi-temporal, contiguous United States air pollution satellite data set with the Area Deprivation Index for a social data set and the inpatient Medicaid claims for a health data set. Wei et al. Found that nitrogen dioxide, ozone, and particulate matter were associated with asthma hospitalizations in populations holding Medicaid insurance who live in deprived areas. Castillo et al.'s Washington, D.C. study is another good environmental epidemiology example that we found. These researchers combined a surface particulate matter satellite data set with social data sets from both the American Community Survey and NASA's Socioeconomic Data and Application Center, and combined it along with the DC Department of Health data set, which includes all-cause mortality and other health risks attributable to air pollution, such as heart attacks, lung cancer, and asthma emergency department visits. Castillo et al. Found that people of color communities living in lower socioeconomic attainment neighborhoods had higher particulate matter exposure risks, which were associated with higher health burdens. When combined with other information, satellite data provides evidence of inequality and injustice. Most studies authors concluded that populations who are non-white and/or those who are experiencing lower income or lower socioeconomic status have the largest inequities in exposure to environmental hazards or the least access to green space, which causes them to have the highest vulnerabilities to health risks and mortality. Ufoma will now further explain how satellite data was used in these studies.
Thanks, Tanya. I will now highlight a few points on the advantages of satellite imagery through a few specific studies that we reviewed. Satellite data provides wide spatial coverage, enabling national studies to be performed. In one study, Casey et al. Leveraged this to look at nationwide disparities in green space. Satellites can measure green space through a metric called the Normalized Difference Vegetation Index, or NDVI, which indicates presence and health of vegetation. Some commonly used instruments include NASA satellites Landsat and MODIS. These satellites provide a long temporal archive enabling time series analysis, such as change in NDVI for different regions. Studies can thus show large-scale and long-standing disparities in distribution and access to green space for certain population groups, such as those that are non-white, foreign-born, and/or of lower socioeconomic status. Other studies benefited from using satellite data measurements in areas that have sparse ground monitors. For example, Lee et al. Used Terra MODIS to model air temperature at a high-resolution scale of 1 kilometer. They showed that this high-resolution temperature data yielded stronger relationships between temperature and mortality than when using the more sparse temperature data. They further found strong trends of temperature-related mortality for Black populations, elderly and isolated populations, and in urban areas. Another understated advantage of satellite data is the ability to assess how multiple environmental categories interact with each other. Several studies that we reviewed showed that lower socioeconomic status was associated with higher air pollution burdens and mortality. Son et al. 2021 introduced satellite-derived green space to see how that modified the relationship between socioeconomic status and air pollution-related mortality. They found that less green space was generally associated with higher air pollution-related mortality for all population groups, with lower income groups having the highest associations. While green space is commonly accepted as a benefit on its own merit, this study also shows its potential to mitigate some other health disparities. Another insight on the use of satellite data pertains to the study design of the reviewed articles. We found that there was a nearly equal proportion of studies that were cross-sectional, meaning they were performed at a single point in time, as there were multitemporal, referring to time series analysis studies. This shows that in general, the temporal archive of satellite data could be further leveraged. This figure illustrates how, for example, NASA's Landsat satellites provide approximately 50 years of historical data. Multitemporal analysis in environmental justice is important to consider as it can support characterization of cumulative impacts, which refers to the multiple environmental and social stressors communities face over time that can increase vulnerability. Now I will highlight how satellite data specifically benefit public health and policy interventions. Satellite data can inform real-world impact of environmental policies like the EPA's Clean Air Act. For example, Curie et al. Used multi-temporal satellite data and population data from the US Census to show the efficacy of the Clean Air Act in reducing racial disparities in air pollution exposure through spatially targeted air quality regulations across the United States. This figure plots mean particulate matter 2.5 exposure by year separately for African Americans and the non-Hispanic white population. The gap between PM 2.5 for the two groups has remained constant since approximately 2007. And what the study shows was that despite the reductions that in an absolute sense had larger benefits for the Black population, there is a persistent difference in exposure between the populations. Satellite data was also used to evaluate equity of heat mitigation planning in Detroit, Michigan. One study used land surface temperature data from Landsat to identify if the hottest parts of the city would benefit from urban greening efforts and how heat and greening overlaid with different population groups. They found that Black, Hispanic, and Asian populations have the highest heat exposure. They also found that although existing green roofs were in the most affluent areas that weren't as heat affected, through the new greening program, Black populations would have the highest access to green space. The ability to link satellite data with health data can also improve public health monitoring and screening tools. Several tools, such as the CDC's Environmental Justice Dashboard and California EnviroScreen, already include some amounts of satellite data. With our review's findings that higher spatial resolution data can yield more refined understandings of the distribution of environmental burdens and on the benefits of multi-temporal data, we suggest more agency-level adoption of satellite data as an input into screening tools for more accurate and timely detection of communities affected by environmental hazards. This is just a snippet of the findings from the review, but overall, we show how research using satellite data can contribute to efforts to identify disparities and support targeted interventions. Please look out for the preprint and the published paper soon. Thank you.
Thank you so much, Tanya and Ufoma, for that great overview of how satellite observations can be used to explore environmental justice issues. In this next part, we'll hear 3 presentations on different environmental justice issues, which can be assessed using satellite remote sensing data. First, we'll hear from Xiaoxian about light at night.
Thank you. Hi, everyone. My name is Xiaoqian. I am an associate professor in the Department of Epidemiology, Human Genetics, and Environmental Sciences at the University of Texas Health Science Center at Houston. So today I am going to talk about our work that focuses on light at night. I hope to explain to you why this is an important public health and environmental justice issue. So just a little introduction. As we all know, the nightscape of our planet has been drastically changed since the invention of electric lighting. On this slide, you can see this image of the United States that was taken in 2013. And you can see all the bright spots that indicate large cities with high levels of light at night. And you can also see little spots that are smaller cities and also the even smaller ones that line the major highways. So the reason that we're interested in light at night is first because it's everywhere. It's really this ubiquitous environmental exposure. And despite the tremendous benefit of light at night, there are also serious ecological, economical, and public consequences associated with electric lighting. And why we think light at night is a public health hazard is because light at night can suppress melatonin, which is a very important hormone that regulates sleep, circadian rhythms, and many other behavior and physiological processes in humans, and also in plants and animals. And also, having light at night can enable nighttime activities that are not always well aligned with our biological clock. In fact, epidemiological evidence has convincingly linked light at night with a number of health problems, from sleep deficiency to obesity to cancer. Moreover, light at night has also been shown as an environmental justice issue. So this is one of the first studies, not by our group, that have investigated light at night as an environmental justice issue. And from this quote that I took from the study, basically what it showed is the racial and ethnic minority populations in the United States are exposed to higher levels of light at night when compared to white Americans. So what we decided to do is to expand this line of research to look at the relationship between light at night and social vulnerability. So not just the racial ethnic composition of the neighborhood, but social vulnerability more generally. And we took this nationwide analysis where we used the light at night data which was obtained from the Black Marble data suite for the period of 2012 to 2019. So those are satellite-based estimates of artificial light at night. And the vulnerability measure we used is this SVI, Social Vulnerability Index, which is an index developed by the CDC. And this index gives you an overall value for the total level of vulnerability in the neighborhood. And also you can divide that into 4 components, each representing a specific aspect of social vulnerability. That includes socioeconomic status, household composition and disability, minority and language status, and housing and transportation. So the objective of our study is to conduct this analysis at census tract level to evaluate the relationship between light and night and social vulnerability. And I should mention that we have derived the summary measures of light and night based on the Black Marble data suite, and those tract level and county level light and night data have already been provided and published by NASA. So if that's something you're interested, please contact us and I'd be happy to direct you to the useful links to get that data. So as I said, the objective of this study is to examine the overall association between light and night and social vulnerability, and also to examine whether or not this association differ by rural-urban status and across different regions of the United States. So on this slide, I'm showing you the overall association between social vulnerability, which is presented on the x-axis, and light at night, which is presented on the y-axis. And as you can see, there is a significant and positive relationship between the two, which means the higher social vulnerability experienced by a neighborhood, the higher light at night that occurs in that neighborhood as well. So next, we looked at this relationship by each component of social vulnerability. So as I mentioned, there are 4 of them, each represented as this open circle in this panel under the previous panel. And as you can see, for the 4 components, now we're comparing the highest quintile of vulnerability with the lowest. And as you can see, we see this positive relationship between higher vulnerability for the components of socioeconomic status, minority and language, housing and transportation. But we really don't see any association between light and night and household composition. If anything, the relationship is slightly negative rather than positive, which really suggests this relationship varies across different components of social vulnerability. Not all components are universally associated with light at night. So next, to complicate the picture even more, we looked at this relationship across different rural and urban status, and as I said, across different regions. So the first thing we found is that this association between light and night and overall social vulnerability was again not universal across different tracts with different rural urban status. What we found is that the positive relationship I showed you before was really only observed in the cores, the urban cores, so that means the cores of the metropolitan areas and micropolitan areas, and also the cores of small towns as well. However, we really didn't see a relationship between the two in the suburbs of the urban areas. Interestingly, we found a pretty strong positive relationship between the two in rural areas, which are not really reported before. And we also dived into each component of the social vulnerability index, and we also found differences in the associations across different rural urban status as well. And finally, we did observe regional differences when we looked at the 4 regions across the states. That's the Northeast, Midwest, the South, and the West. So by the way, I'm not presenting the specific data here, but if that's something you're interested, the paper has already been published, so you can check it out. And it's published in the Journal of Environmental International. So in conclusion, from this analysis, we found that overall, more vulnerable communities are exposed to higher light at night. However, the relationship is very complicated. It differs by social vulnerability components, rural urban status, and regions. And what this reminds us is when it comes to identifying communities with highest light pollution or other environmental hazards, it's really important to consider multiple factors for characterizing those communities. And for us, a future direction is to really understand how this environmental injustice in light at night, or this uneven distribution of light at night, may have contributed to health disparities in this country. And finally, this is the last slide, and I just want to remind you that when we study environmental justice or injustice, it's not really just about uneven distribution of exposures. It's also about the uneven responses to the same exposure. So when you think about people living in disadvantaged neighborhoods, oftentimes not only are they exposed to higher levels of hazardous exposures, but also they tend to have a higher response to those hazardous exposures. So on this slide, what I'm showing you is a previous paper that we published that looked at the relationship between light at night and breast cancer risk. And we divided our analysis in this large US cohort by poverty rate at the tract level. And here you can see the solid line represent the tracts with a low poverty rate, so more affluent tracts, and the dashed line represent high poverty areas. And when you look at the relationship between light at night and breast cancer risk, you really don't see any relationship among those more affluent tracts. But you did see this positive relationship where light at night is associated with higher risk for breast cancer among women who lived in high poverty areas. And we speculated that, this higher response to light at night among those women from poor communities could be due to a number of factors, including poor housing or sleep conditions, their challenging work schedule, just general higher levels of stress, all of which may exacerbate the adverse effects of light at night on breast cancer risk. So with that, I just want to conclude that we believe light at night is an important environmental justice issue, of course, also a public health hazard. And it's important to identify vulnerable communities that are exposed to higher levels of light pollution, and also for us to develop, implement, and evaluate potential interventions to mitigate the hazardous exposure to light pollution and to mitigate the health disparities associated with this exposure. So that's all. Thank you.
Thank you. Our next presentation is by Danielle Wood and Ufoma Ovemida, who will discuss the Environment Vulnerability Decision Technology, or EVDT framework.
Hello, everyone. My name is Professor Danielle Wood. I'm from the Massachusetts Institute of Technology.
And I'm Ufoma Ovemida. I'm a PhD student at the Massachusetts Institute of Technology.
Thanks, Ufoma. We both represent the Space-Enabled Research Group at MIT, where we work toward asking how we can use technology from space to support sustainability and justice on Earth. Today, I'll be sharing an example of how we use space technology, particularly satellite data, in justice-related applications. In particular, I'm excited to highlight a tool set we use called the Environment Vulnerability Decision Technology Framework to support social and environmental sustainability. We call it EVDT for short. That stands for Environment Vulnerability Decision Technology. The motivation for this framework is that there is a great set of satellite technology available. In particular, here I'm highlighting the examples available through NASA, but of course, globally speaking, there are many satellites of different types that provide observation of what's happening in the atmosphere, on the land, in the oceans, and help us understand how the environment is changing. Now, this multiple types of satellite data are also challenging to use, partly because there's an important supply chain that's needed, or value chain, you could say, to move the data from the original observations into use. Often the ultimate goal is to provide information that is recommendations for action by policymakers. To make that happen, we need satellite systems, as well as systems in atmospheric operations and on the land and in water, producing data. But also scientists play key roles to help correct and process the data, do modeling and assimilation, and help combine this Earth observation data with socioeconomic and other kinds of data to really answer social questions. There's a lot of work at each of these stages, and often private organizations play a key role in steps 6, 7, and 8, especially in the US context. One of the motivations for my team is to ask how we can help make this kind of value chain or series of work steps more available, especially to those that usually do not have access to using the rich information available from satellite Earth observation. In my experience, I've had a chance to learn from leaders in countries, especially in Africa, but also Latin America and Asia, including in places like Kenya, South Africa, Angola, Nigeria, and other countries. They are countries that have shown me that they're interested in using satellite mapping to help improve policies in their country, and they look for ways to reduce the barriers to people in their own countries using the data. The same thing is true in my home country in the US, that there are many organizations that have policy questions that could be addressed in part by information from satellites, but there are many historic reasons why it's difficult to access the data when needed. In some cases, the countries that I work with are applying tool sets such as the Sustainable Development Goals as defined by the United Nations as a way to identify what methods they're working toward. In other cases, countries or leaders in companies or perhaps Native American tribes are also exploring other internally defined methods for deciding what is helpful and what they consider a societally important goal. One of the goals of my team can sometimes be to ask, how do we know if we're making progress toward the goals defined by each community? And are we reducing the barriers to using satellite data to make that progress? One of the ways we address this question is through a series of methodologies that are inspired by system engineering. We call it system architecture, and here's a brief summary. It has steps including understanding the context of the organizations that we're working with, asking their stakeholders to define what's important to them, identifying objectives, and then the functional and sort of forms that we'll design for an information system using satellite data. Our goal in these steps is to make sure we're listening carefully to the concerns raised by organizations, whether they're national governments, university teams, or companies that are trying to address a societal need that has typically had barriers in using satellite data. So we use this as a way to make sure we're listening to stakeholders to ensure that the methodology will be useful from their point of view. This has led us to also design the EVDT, or Environment Vulnerability Decision Technology Framework. It allows us to ask questions such as what's happening in the environment, how are humans experiencing vulnerability and societal impact, what human policies are impacting both the environment and humans, and how can technology be designed more effectively in order to make it more useful. In particular, we often ask how we could design satellites, aerial platforms, and in situ measuring platforms to help inform our understanding of the environment and the human impacts. And again, this is really important as researchers that we do this in a way that's driven by listening carefully in a very structured way to our collaborators who have certain goals for what they're trying to achieve in society. And in some cases, those goals are well aligned with environmental justice goals. I want to give a few examples where teams are working either on sustainability goals or environmental justice goals as they define them. Particularly, the city of Rio de Janeiro, for example, leaders from Indonesia, the government of Angola, and the Yurok tribe in Northern California. They've each invited us as a team, as Space Enabled, to collaborate with them to apply satellite data to particular needs. Again, the needs are defined by them in a way that makes sense to their community. And we try to consider if we are aligned with those values and try to see how we could apply satellite data with them. I give a brief example on the case study in Angola, and this is funded by NASA's Applied Sciences program, in particular from the Water Resources Management program. We are funded to work on the application of satellite data to help support drought response in southern Angola. It's an area affected by long-term patterns of recurring drought and flood, and this affects local communities who depend heavily on raising cattle as a form of livelihood. I've been invited by the National Agency for Space to visit the country and learn about their needs and to ask how we can reduce barriers to using NASA satellite data to understand the impacts of the drought on low-income communities. The country is active in their own space program. You see me here focused on visiting the local space agency, and they're celebrating their recent activities with satellite technology, and they're really ready to increase their use of satellite data. In particular, we're using NASA SMAP, or Soil Moisture Active Passive Data, because it has a sensor that uses microwaves to reflect light from Earth and helps us understand the impact of lack of rainfall on the level of water in the soil. So eventually we'll make these kinds of systems that map the level of drought intensity in Angola for multiple years using data from SMAP. So in a picture like this, you can see the dark red areas have very dry soil. And we're gradually improving our ability and reducing our error in estimating this for the region. But this is not the end. We also need to combine that with data related to socioeconomic variables that impact, understanding who's impacted by the drought. So in this case, we're trying to understand how to combine the information from space with local variables that the teams in the country can develop so they can figure out how to best provide responses that serve the communities locally. This is one way we think about listening to the community's needs and asking how we can use that information to make satellite data more effective, but in a way that's really concerned with the needs of those who usually have less access to data. Ultimately, we make websites that are very useful to help make this information available for policymakers. To summarize, we found it useful to customize EBDT to this case study in Angola. And each time we work with new partners, we make a new custom version. And this can be a great template for future work that addresses societal needs with satellite data. I'm now pleased to pass this over to my colleague, Ufoma Oyemura, who's going to continue with an example in her own research.
Thanks, Danielle. I'll be talking about an example of how we can apply the EBDT framework to study prisons and environmental justice. So this is an example of Fayette Prison in LaBelle, Pennsylvania. It's an aerial view of the prison. Fayette is built near about 40 million tons of waste, 2 coal slurry ponds, and millions of cubic yards of coal combustion waste. This pollution is often associated with air pollution. It's also associated with health effects. Incarcerated people at Fayette have documented numerous cases of skin rashes, gastrointestinal diseases, respiratory illnesses, and cancer that developed after being incarcerated at this prison. This environmental burden and the associated health effects is not unique to Fayette. Over the last few years and decades, scholars and journalists and activists have been documented a pattern of prisons being co-located with a range of environmental burdens, such as air pollution, heat, among other environmental hazards. In this work, I look at an example of air pollution co-located with prisons. And specifically, I'm looking at the limitations of federal air pollution data and how we might leverage satellite-derived data. So the federal and several state governments use data that fuse concentrations simulated by the Community Multi-Scale Air Quality Modeling System, or CMAQ, with ground monitor observations at a relatively coarse resolution of 12 kilometers. This resolution is too coarse to fully resolve disparities in urban areas where more than 80% of the US population lives. In addition, the vast majority of counties have 0 or 1 ground monitor, which may affect the model estimates as air pollution concentrations can vary dramatically over short distances. So I asked the question, are the air pollution burdens of some carceral facilities obscured due to the limitations of model data used in federal tools? This question is particularly important because this federal model data that I'm mentioning, this is used by the EPA's EJ Screen tool and the Council on Environmental Quality's new Climate and Economic Justice Screening tool, or CJEST. And in our methodology, we compare a 1 kilometer satellite-derived PM 2.5 dataset, or particulate matter 2.5 dataset, to the dataset from the CMAQ-F model used by this federal government data that I'm mentioning. In comparing the analysis, we specifically were looking at, for each facility, how does the air pollution burden compare to the statewide air pollution burdens. This thresholding facility of looking at percentiles of a respective state is what is used in EJ Screen. And in total, we identified 42 carceral facilities with higher PM 2.5 air pollution burdens than at least 80% of their respective states. And in the bottom left, you can see that actually 14 were above the 90% percentile of their respective states. Some of the facilities that we identified above these thresholds included those that were directly across from a landfill, in close proximity to dozens of hazardous facilities, and in some other cases were in areas that had really high wildfire risk and had past wildfires just in the last few years. We also saw that the differences in the percentiles for the PM2.5 burden between the two data sets can be quite large. You can see on the bottom x-axis is the percentile, the y-axis is showing some examples of facilities. You can see that the disparities between some of the percentiles can be as high as 70% in some cases. So again, you're seeing a very big difference in what the different data sets are capturing in terms of air pollution burden. In terms of how the EVDT framework can be used to pursue environmental justice, I'll just briefly walk through that. So in our case, the environment model is considering satellite-derived PM2.5. In terms of human vulnerability, we're interested in the facilities that are affected, as well as the population, sociodemographic, and associated health characteristics of those facilities. In the decision-making module, we might consider, are there mitigation protocols already in place or that could be in place? Which facilities need to develop new evacuation protocols? And which facilities have such high burdens that they should really be considered for closing the facilities altogether? And lastly, in the technology design module, which we don't always use, in this case, we might discover that to improve a decision, we might want more higher quality, localized air pollution data, and might want to consider something like air pollution sensors or a airborne campaign, etc. But this isn't always the solution, as technology doesn't always improve the pursuit of environmental justice outcomes. In summary, the satellite-derived dataset can identify carceral facilities likely experiencing poor air quality that might be missed by more coarse federal data. Federal funding initiatives, such as the Justice 40 initiative designed to address environmental disparities, may be discounting the conditions experienced by some people who are incarcerated. And satellite-derived data can contribute a new perspective for environmental justice applications. Thank you.
Thank you, Danielle and Ufoma. Our last presentation is from Daniel Carrion, who will discuss the temperature and energy justice mapping tool.
Thanks so much for that introduction. I'm excited to tell you a little bit about the work that we have been up to. I should first say before I jump in that the work that I'm going to present on is actually funded through NASA's Equity and Environmental Justice portfolio. And so I'll be telling you about the theme of that work, or the topic of that work, which is our temperature and energy justice mapping tool that we are currently calling this project. And as background here, we all know with the threat of climate change that we need to decarbonize our society. There are many different pathways through which we can decarbonize, and we need to take many of these together. And some of those include energy efficiency and conservation efforts and electrification efforts, amongst others. But I'm going to focus first, I'm going to focus for this project on those two. And within that, I'm going to focus specifically within the residential sector. So we know that home energy accounts for 20% of greenhouse gases in the United States, and actually half of which is from heating and cooling. That latter demand being very important as we think about increasing global temperatures and the threats on human health. And so this is a real opportunity to be thinking about household energy efficiency efforts and household electrification efforts. But much like many of the issues with our society, we have many entrenched social disparities, including residential segregation. And residential segregation is a really important nexus point to be thinking about because it represents the intersection of both environmental and social disparities being co-located in space. There are many such disparities to be thinking about within the context of residential segregation, some of which I think about regularly are around air pollution, extreme temperatures, and also energy insecurity. Energy insecurity, if you're unfamiliar, is a framework that outlines the interplay between energy needs, financial constraints, and behavioral adaptations. While there's a robust theoretical framework here, I think this is pretty intuitive to most folks through what's often referred to as the heat or eat dilemma. This is the precarious situation that poor households are often placed in to either keep themselves warm during the winters or eat a nutritious meal as being an example, but there are many such trade-offs that families can be thinking about during this time frame. What I've been increasingly saying is that in a warming climate, we need to be talking more about what I term the heat stroke or go broke dilemma, that same kind of trade-off framework that people may be dealing with, but on during the cooling season or during summers. And one of the factors that people often talk about with energy insecurity is this notion of energy rationing, that people may be cutting back on their energy demand in order to pay for other things as part of that those trade-offs. And indeed, there is evidence of energy rationing at the household level. This particular study being done in Arizona, finding that low-income households wait to higher temperatures to start using more energy, implying that they're waiting till warmer temperatures in order to keep their homes cooler during higher temperatures. So while I won't go into major detail about this paper that I'm going to refer to here, but you're welcome to look at it afterward, what we argue in this paper is when we create a geospatial statistical model to reconstruct fine scale temperatures in space and time, what we find is that we do a better job in a limited application of reconstructing the relationship between social vulnerability and temperature. And so what that implies to us is that finer scale spatiotemporal models can do a better job of reconstructing temperature disparities potentially for the most vulnerable communities. And so taking all of that together, we decided to then try to employ all of this knowledge to try and create a temperature and energy justice mapping tool. This is a feasibility study through NASA, and it's a partnership with the Green and Healthy Homes Initiative. The Green and Healthy Homes Initiative, or GHHI for short, really focuses on addressing household level disparities, originally focused around disparities around lead in the household, but increasingly doing work around energy efficiency in the home and other concerns around residential disparities. And so having this as a stakeholder group, we decided to try and use earth science products and remote sensing data to identify the intersection of localized temperature disparities, social vulnerability, and also markers of energy insecurity, in this case specifically evidence of energy rationing. And the overall goal of identifying these intersections is to be able to potentially support targeted energy efficiency upgrades to the neighborhoods and communities that need them the most. So in order to do this, we are using products to identify temperature disparities. And so this is constructing a heat index using daymet data. Daymet provides us both dry bulb temperature, but also vapor pressure that we can use together to create a heat index. And then we also use land surface temperature. And then we use both of these to create what are called cooling degree days. I won't go into depth about what this measure is, but you can look it up. NOAA has a good explanation on their website of cooling degree days. But quite simply, cooling degree days are a measure of how much hotter a season is than a threshold temperature, typically 65 degrees Fahrenheit. We also use NASA CDAC's Social Vulnerability Index, which is based on the CDC's Social Vulnerability Index. And then we also use energy data from the New York State Energy Research and Development Authority, or NYSERDA for short, their utility energy registry, which has historical energy data at various spatial scales. So some very preliminary results from our work. This is essentially a plot looking at kernel density smooths of temperature throughout the climate regions of New York State. And what you can see here is that zooming into various climate regions, we can see evidence of temperature disparities that are pronounced in some areas and perhaps not in others. So for example, in the East Hudson and Mohawk Valley, you can see that the temperature distributions seem much higher for Hispanic Latine folks, Black folks, and also for Asian folks compared to white folks, whereas those patterns don't seem pronounced, or perhaps even in the opposite direction in the Adirondack Mountains. And so this really is just an example of why fine scale resolution models help us to reconstruct what's going on in the local areas and communities. Also looking at that residential energy data that I mentioned before, this is not the result of analysis, but just plotting what that residential energy data looks like at the zip code level. This is characteristic of what people often refer to as the Falcon curve, where we see the highest levels of energy use during the winter, but then also during the summer. And in some preliminary regression analyses, what we do is we look at those cooling degree days at the zip code level, and then look at the energy use at the zip code level. And what we find is that zip codes that are in the lower part of the income distribution, so the 25th percentile of the income distribution, seem to use lower amounts of energy at equal cooling degree days, which to us implies this energy rationing that I was referring to earlier. So there are many different potential policy implications here, including informing policies like the Low-Income Home Energy Assistance Program, which is one of the only energy assistance programs that exists in the United States at the federal level, other energy protections at the local municipality level, and then the chief goal of this work is to potentially inform targeted energy improvements through partnering with our partner, the Green and Healthy Homes Initiative. So this is not possible without many of our collaborators, including those from the Green and Healthy Homes Initiative, also at Yale University and at Brown University. Thank you.
Thank you, Daniel, and thank you to all our other guest speakers. Hopefully these presentations have given you an idea of the scope of different environmental justice issues that can be assessed using satellite remote sensing data, as well as some of the benefits and the challenges of using satellite data in these applications. To briefly summarize what we've just heard, The strengths of remote sensing data for environmental justice applications include the ability of satellites to provide information in many areas where ground-based data may be lacking. We saw an example of this in the Prisons Project, presented by UFOMA, where the exposure of individuals in these facilities was poorly represented using ground-based data, and satellite information was useful in identifying localized disparities in exposure. Satellites also allow us to provide continuous global monitoring using the same instruments over long periods of time. We saw an example of this in Danielle's presentation on drought monitoring in Angola, where it was possible to create a multi-year drought record from satellite data to look at trends in water availability. The ability to monitor around the world using the same remote sensing instruments allows us to make robust comparisons between different areas, as we saw in Danielle's presentation about the disparities in heat exposure across different parts of New York State, and in Xian's presentation about exposure to nighttime light across different regions of the US in different population groups. The data collected by NASA using remote sensing are also freely available, and NASA provides tools to assist in the analysis of these data, as well as trainings like this one in how to make effective use of the data for different applications. You heard about the impact this is having in terms of the growth in the use of satellite data for environmental justice studies in Tanya and UFOMA's presentations earlier today. Finally, satellite data can be integrated with other information sources, such as models and ground-based data, to produce combined data sets, which improve our understanding of environmental issues across space and time. You'll hear more about how this is being done for air quality from Susan Annenberg in just a minute. Of course, we also have to acknowledge that satellite data have limitations. It's very difficult to obtain fine spatial resolution, fast data collection frequency, and wide area and long-term coverage, all from the same satellite instrument. We may need to pull together data from multiple sources to meet our data needs for a specific application. Or it might be that no existing satellite data sets meets our requirements. Working with satellite data can also be challenging. Although NASA provides many free online resources and trainings such as this, there are still technical barriers to using satellite data, including the need to process large amounts of data and handle diverse file formats. Finally, while satellite data are validated extensively using other available data sources, especially ground-based measurements, this validation cannot be done always and everywhere, and various factors like changes in land cover can impact the quality and accuracy of satellite data. For specific applications, wherever possible, we encourage that additional validation be done to verify that conclusions drawn from satellite data are lining up with what is being observed on the ground. I'm now going to hand us over to Susan Annenberg, who will present a more in-depth look at how satellite data have been used in air quality environmental justice applications in particular, including the benefits and drawbacks of using satellites in these specific applications.
Thank you. I'm going to talk about use of satellite data in environmental justice applications. I'll first talk about a case study using satellite data to understand air pollution in justice. There's a long history of studying air pollution in justice, and in more recent years, people have started using big data to study this problem. And I just want to give two examples of how people have used big data to study air pollution in justice. In the graph on the left, this is from Culmer et al., which was published in Science in 2020. And they found that the communities across the United States that were overburdened by PM 2.5 in 1981 are still overburdened by PM 2.5 in 2016. And this is despite the fact that PM 2.5 levels have dropped overall. So those areas that were most and least polluted in 1981 remain so today. The second study I want to highlight is Tessem et al., which was published in the Proceedings of National Academy of Sciences in 2019. And they found large differences between the environmental health damages caused by a racial ethnic group and the damage that group experiences. So just take a look at the two bar graphs on the left-hand side of this chart here. The Black population in the United States is exposed to much larger PM 2.5 concentrations than it causes. That's consistent with the Hispanic population and opposite to the white population on the right-hand side here, where the white population is exposed to lower PM2.5 concentrations than the PM2.5 that it causes. And because this study used a modeling approach, they were able to also look at the sources that were contributing to this PM2.5 inequality, both in terms of the emitters and the end uses. So these are two examples of how big data can be used to understand air pollution injustice across an entire country. But when we talk about big data, what do we mean? There's a lot of different ways to characterize air pollution exposure. We have ground-based monitors, and this is an example picture of a federal reference monitor. These are costly and resource-intensive ways to measure air pollution in the air at a particular point in space. We have sensor networks, and increasingly these are low-cost sensors. Each of these costs about on the order of a couple $100, which is significantly less than the federal reference monitors shown on the left-hand side of this slide. And because these low-cost sensors are much cheaper, you can put dozens to hundreds of these in an individual urban area. Sensor networks, these low-cost sensors, they're challenged by issues like calibration and drift, and so they do still require some caution and rigor in interpreting, but it's a really nice way of getting at neighborhood scale pollution differences across an urban area. The third approach to characterizing air pollution exposure is models, and we have both statistical models and physical models. But these models divide the world into pixels, both in horizontal space and in altitudinal space. And they use a series of equations to estimate pollution concentrations in each pixel. So these are not observational. This is an estimation approach, and statistical models use a series of statistics and equations to try to estimate pollution levels in each pixel. And physical models use our best understanding of the physics and chemistry of the atmosphere to calculate pollution fate and transport, and again, estimate pollution in every pixel on the planet. And so this is a nice way to estimate exposure for everyone on the planet, regardless of whether or not there's a nearby monitor. And the final way I want to highlight of characterizing air pollution exposure is, of course, satellite remote sensing. Satellites orbit the planet and they're taking snapshots of the composition of the Earth's air. And we can use these data to understand pollution levels and how they vary with increasingly high spatial resolution. And we're going to talk about this, of course, in much greater detail. But what are some advantages and disadvantages of ground level monitoring? Well, ground monitors are still considered the gold standard today. They're the best estimates of air pollutant concentrations, especially if you're using a high cost instrument like these federal reference monitors. Measurements are also acquired at the nose level where we breathe, which is of course of interest to us because we want to ensure that we have healthy air for everyone to breathe. And monitors, and not models or satellites, are used by regulatory agencies to determine attainment with standards, with ambient air quality standards. So for example, the US Environmental Protection Agency, they use monitors to determine whether or not any given area is in attainment with the national ambient air quality standards. And so far, models and satellites cannot be used for that purpose. But of course, monitors have disadvantages as well. They were not set up or intended to measure how pollution levels differ within urban areas, and therefore they're interspersed. There's often approximately one monitor per 500,000 people, which is really not enough to capture neighborhood scale pollution differences. They also really need careful calibration. That requires a site visit by a technician at least once per week. And they have some siting restrictions as well. They can only be located on land. They're sited to capture regionally representative levels of pollution and not how pollution varies at the neighborhood scale. And some are not required to operate all year round. When it comes to satellites, satellites also have advantages and disadvantages. One of the advantages is that estimates are available for anywhere where there are no clouds and reflective surfaces. So we still can't see through clouds, and reflective surfaces pose a problem when using satellites to characterize air pollution. But for the most part, you can get an estimate anywhere on the planet, regardless of whether or not there's a ground monitor located there. We can achieve complete geospatial coverage if we combine what the satellite sees with other information like land use variables near roadways and parks and other types of green space. And we can also combine satellite data with measurements from the ground. and get increasingly high spatial resolution and high accuracy as well. So with satellite data, we're getting to the point where we have pretty high accuracy at about 1 kilometer spatial resolution, and that enables us to look within individual urban areas at how air pollution varies. For some pollutants like nitrogen dioxide, we also have a very high correlation between satellite estimates and ground monitors. So what the satellite is measuring is the total amount of pollution from the ground level all the way up until the satellite. That's what we think of as a column of air. With nitrogen dioxide, there's a really high correlation between the satellite estimates of those column measurements and the surface level concentrations at the ground. But satellites also have disadvantages. Right now, we can't observe all chemical components in the atmosphere, so there might be some pollutants that are of interest for environmental injustice. Hazardous air pollutants come to mind, where we don't have high quality estimates from satellites yet. We also can't monitor surface concentrations. As I mentioned, satellites monitor molecules in a column of air between the Earth's surface and the satellite. And that has to be combined with other information to produce health relevant estimates at the nose level. And that can be quite data intensive. So this does still require quite a bit of number crunching and data manipulation to estimate ground level pollution concentrations from surface observations. Right now, most satellites are polar orbiting. They're taking one snapshot over every location on Earth each day. But new launches are happening and planned as geostationary. And that means the satellite will hover over one part of the planet and take snapshots of the Earth's air on an hourly basis. And therefore, we get full daytime coverage over one particular region of the planet, like the United States. So which air pollutants are measurable from satellites? Well, a lot of us are concerned about fine particulate matter, or PM2.5, which is the largest contributor to the mortality burden from air pollution. But we can't measure PM2.5 directly from satellites. We have to convert something called aerosol optical depth, or AOD. We also can use satellites to detect fires, which produce a lot of smoke and PM2.5. And both of these aerosol optical depth and fire detection can be used to infer nose level PM2.5 when combined with other information, like from atmospheric models. For ozone, this is another major air pollutant that is highly regulated. There's currently no information on nose level concentrations from satellites for ozone because stratospheric ozone is so high and really obscures that signal. Nitrogen dioxide, or NO2, is the most straightforward to observe, and it's an excellent tracer of fossil fuel combustion. So I'm going to talk in this section of this training about nitrogen dioxide and how satellite-derived NO2 can be used to study air pollution and justice. And then we have a range of additional chemical components, pollutants, for which precision and accuracy of the satellite data are not currently suitable for most health studies, and that includes carbon monoxide, sulfur dioxide, ammonia, formaldehyde, and also surface ultraviolet radiation. One of the first studies that we did to try to use satellite-derived pollution levels to understand air pollution and justice was in partnership with the DC Office of Health Equity and the DC Department of Energy and Environment. That's in the city of Washington, DC. And this is motivated by the dramatic health inequity that we see in the District of Columbia. The DC Health Equity Report was published in 2018, and it found about a 20-year life expectancy differential between communities in the southeast quadrant of the city and communities in the northwest quadrant of the city. And you can see that in the size of the red bubbles. If you look at the underlying green colors, we also see that there's quite a large discrepancy in the pediatric asthma emergency department visit rate per 10,000 in the city, with the highest rates in the southeast quadrant neighborhoods compared with in the northwest. Now, what if we wanted to know how much air pollution contributes to this health inequity? What data sources could we use? Well, let's take a look at a map of air pollution monitors, that is federal reference monitors in the District of Columbia. And there's 5 of them for PM2.5. It looks like 4, but 2 are co-located. So we don't have enough ground level monitors in the city to really understand what is driving or how much air pollution is driving this 20-year life expectancy differential between neighborhoods in Southeast versus neighborhoods in the Northwest. So we use satellite-derived PM2.5 concentrations, and you can see those concentrations in the map on the left-hand side here. And we see that we have continuous spatial coverage of PM2.5 on a pixel basis across the entire city of DC. And this was published in the journal GeoHealth in 2021. When we combine information from the satellite-derived PM2.5 with the life expectancy in the previous slide, we can estimate PM2.5 related mortality rates at the neighborhood scale within the District of Columbia. And that's what you're seeing in the map in the middle here, where we have the highest PM2.5 mortality rates in the eastern half of the city, which is majority Black, compared with the western half of the city, which is majority white. And so this really showed us two things. One is that we can gather a lot of information using satellite-derived air pollution concentrations. And when we combine that with the inequitable distributions of health risks, we really get a very large inequity in air pollution-related health risks across the city. But if you look at this map of PM2.5 concentrations on the left, we still don't have as much heterogeneity, as much spatial pattern of PM2.5 that we believe exists within the urban scale. Scientists have been combining satellite-derived data sets with other information like land use variables to really enhance that spatial resolution. So if you look at the map on the left-hand side here, this is PM2.5 in New York City, which was published by Huang et al. In Science of the Total Environment in 2019. And you can see that there's quite a bit more spatial variation in ground level PM2.5 concentrations with their model, which uses both satellite observations and land use variables and ground level monitors in an integrated way. And they can capture much more spatial heterogeneity than we were able to in our previous study of Washington, DC. We can also do this for nitrogen dioxide, and that's shown here on the right. This is data from our study that was published in Lancet Planetary Health in 2022. And you're seeing Washington, DC with high NO2 concentrations in the downtown area, but then all the roadways going out from the downtown area to the suburban areas in Maryland and Virginia and all the way up to Baltimore. All of those major roadways also have high NO2 concentrations when we put the satellite data together with land use information in a model. So to study air pollution and justice with satellite-derived NO2, why do we want to use satellite-derived NO2? NO2 is a precursor to PM2.5 and ozone, so we care about it. If we want to reduce both PM2.5 and ozone, we have to be thinking about NO2 and its precursor NOx emissions. And NO2 is also a marker for traffic-related air pollution, which is associated with respiratory effects, cardiovascular effects, and even premature mortality. So there's a range of health outcomes that we're concerned about when it comes to nitrogen dioxide. Compared with total PM2.5 mass, NO2 also has sharper gradients near emission sources. It has a shorter atmospheric lifetime, hours compared with days for PM2.5, and also less influence from regional pollution sources like agriculture and wildfire smoke and dust, which drive a lot of the PM2.5 in urban areas. For NO2, most of the NO2 in urban areas is from emissions coming from emission sources within that city. And that's not necessarily the case for PM2.5, which is driven by upwind sources like from agriculture and smoke and dust. And also a lot of PM2.5 is secondarily formed in the atmosphere far downwind from the precursor emissions. NO2 is a surrogate for urban combustion-related air pollution, including PM2.5 components that exhibit more spatial variation than total PM2.5 mass. And that includes black carbon and also particle-bound polycyclic aromatic hydrocarbons. These are two pollutants that are of great concern when it comes to air pollution and justice. And so we might be able to use NO2 as a surrogate for these PM2.5 components that exhibit more spatial variation. And also, as I previously mentioned, satellite NO2 column observations are tightly correlated with NO2 observed at ground monitors. So we really can tease out the spatial pattern of ground levels of NO2 that people are breathing when we use satellite NO2 columns. So the rest of this presentation, I'm going to dig in a little bit more about how we can use satellite-derived NO2 to study air pollution and justice. This is a picture of the TROPOMI sensor on the Sentinel-5P satellite from the European Space Agency. And this is flying right now. It's a polar orbiting satellite that's taking a snapshot of the atmospheric composition everywhere on the planet in about the early afternoon once per day. And when we use many days of observations from this satellite, we can get a continuous map of nitrogen dioxide from this satellite, as shown on the right-hand side here, which is a map developed by Dan Goldberg from George Washington University. And you see that NO2 in 2019 is really high in urban areas of the world, and also in areas that have large emitting sources like coal-fired power plants. So what do daily satellite data look like? Well, Dan Goldberg also created this website, tropomeno2.us, which you can go to right now if you'd like, and you can get an updated image, an updated map of TROPOME-NO2 observations on any day across the United States. So this is just one day in 2022. And you see quite a bit of noise here when we look at one day of TROPOME data. There's also a lot of white areas, and that's where there are clouds that the satellite can't see through. When we start to average over multiple days, this is a seasonal average, we start to get a much more continuous, less noisy, and more stable estimate of NO2 concentrations and where they're high. And we can use that continuous surface to study air pollution in justice. So let's just zoom in a little bit on the spatial resolutions that we can get here. GOM-2 was a legacy satellite, an old satellite, which had quite a large spatial resolution. And the city of Washington, D.C. was captured in 1 pixel from GOM-2. OMI is a satellite instrument that was measuring nitrogen dioxide launched by NASA. It had about a 20-year lifetime, and you can see that it had a much higher spatial resolution than GOM-2, but NASA has recently just launched TEMPO, which is the first geostationary satellite hovering just over the United States and taking hourly images of NO2 over the United States. And TEMPO is expected to have much higher spatial resolution compared with OMI. The TROPOME satellite sensor that is being used for the map on the right-hand side here has about the same spatial resolution as that TEMPO pixel. So on the right-hand side, this is displaying TROPOME NO2 values averaged over about a 1.5 year period over the cities of Washington, D.C. and Baltimore. And again, we see high NO2 levels in the downtown urban areas, but also high levels radiating outward along the highways going out from these cities. And especially that highway that connects Washington, D.C. to Baltimore, you can see high NO2 levels. Now, this is really almost directly from the satellite. We're not combining the satellite information with any other information at this point. So this is really incredible that the satellite can see not just this urban pollution signal, but even the signal from dense highway traffic of trucks and vehicles traveling between these two cities. So a few years ago, we wondered whether or not we could use satellite NO2 observations to study air pollution and justice on a nationwide basis. And this is work led by Gage Kerr from George Washington University. It was published in the Proceedings of National Academy of Sciences in 2021. And we found that NO2 concentrations, this is using TROPOME NO2 concentrations measured from the satellite, that NO2 concentrations in the least white census tracts across the United States was almost double the concentrations in the most white census tracts prior to the COVID-19 pandemic in 2019. And you can see that in the orange dots depicting NO2 concentrations in the least white census tracts compared with the blue dots depicting NO2 concentrations in the most white census tracts in that pre-lockdown period in 2019. During 2020, during the 2020 lockdowns, about 50% of passenger vehicle traffic came off the roads. And we saw both the orange dots and the blue dots shift left, indicating that NO2 concentrations dropped for both the least white census tracts and the most white census tracts. And yet, we saw that the orange dots in during the 2020 lockdown were still higher than the blue dots in 2019, indicating that even about a 50% drop in passenger vehicle traffic was not enough to eliminate those disparities in NO2 pollution. So the pandemic reduced but did not eliminate NO2 disparities of major urban areas in the United States. And you can look at the major urban areas listed here: New York, Los Angeles, Chicago, Dallas, Houston, and Washington. We see similar results for all of these urban areas, we tried to dig in a little bit and understand what are the emission sources that were contributing to the air pollution injustice. And we found that the proximity of highways and diesel traffic in minoritized communities were a key driver of NO2 disparities. Now, we wanted to take this a step further because it's not just concentrations that we're dealing with when it comes to air pollution injustice. It's also the susceptibility of the populations. People have differential access to high quality healthcare. They have much different rates of cardiovascular disease and respiratory disease, which makes them more susceptible to air pollution. There's a variety of other social determinants of health that are driving the how a community responds to levels of air pollution. So we want to account not just for the concentrations, but also for the health risks when it comes to exposure to those concentrations. So in this study, we were estimating PM 2.5 attributable premature deaths per 100,000 people on the left-hand side here, and then NO2 attributable pediatric asthma cases per 100,000 on the right-hand side. And just take a look at the graph on the left for a moment. For PM 2.5, we see that PM 2.5 concentrations declined over time over this period from 2010 to 2019. And that's in response to our very successful Clean Air Act and the regulations that go along with it. And yet we still see quite a bit of air pollution injustice with higher PM 2.5 attributable premature death rates in the least white census tracts compared with the most white census tracts across the United States. The relative disparity, that line chart on the bottom, has been increasing over time to about 1.32. That's the ratio of PM 2.5 attributable premature deaths per 100,000 in the least white census tracts compared with the most white census tracts. On the right-hand side here, we have the NO2 attributable health impacts, pediatric asthma cases per 100,000. We also see that those are going down over time, but we still have quite a bit of disparity. In fact, much more disparity for NO2 attributable health impacts compared with PM 2.5 attributable health impacts. Here for NO2, we have a ratio of about 7.5. That is that the NO2 attributable pediatric asthma cases per 100,000 are about 7.5 times higher for the least white census tracts across the United States compared with the most white census tracts. And those relative disparities are increasing as well. Now, we've talked a lot about PM 2.5 and NO2 and the value of information from including NO2 in an air pollution injustice study, and the value of including satellite data as well. Let's look at the air quality indicators that are used to map environmental justice. These are the indicators that are in EPA's EJ Screen model. You may already be familiar with this, and I'll explain what EJ Screen is in greater detail. But I just wanted to first mention the indicators that are used in this widely used EJ mapping tool, EJ Screen, which is developed by the Environmental Protection Agency. So in terms of the indicators, the air pollution related indicators currently included in EJ Screen are PM 2.5, diesel PM 2.5, ozone, and air toxics. And they come from a variety of different sources, mostly modeled. The PM 2.5 and ozone estimates are from a model Monitor Fusion. And those estimates have a spatial resolution of 12 kilometers by 12 kilometers. That's really much larger than what we can do with satellite data, where we can get down to 1 kilometer spatial resolution and sometimes even higher. So right now, EJ Screen does not include nitrogen dioxide and does not include satellite data. So this really provides an opportunity to see what kind of information that we can get from incorporating satellite data and satellite estimates of nitrogen dioxide specifically. We now have high resolution data sets that fuse satellite data with physical models, and that allows NO2 to be assessed for individual block groups, and that's what's shown on the map on the left-hand side here. And this block group level NO2 can be directly integrated into EJ Screen to explore inequities associated with this pollutant and compare with existing environmental indicators. So I want to do a quick demo of that. This is NO2 in Philadelphia. Well, it's percent people of color on the left and then NO2 on the right. And there is a correspondence between race and NO2 levels. And when we look at diesel particulate matter instead of NO2, we see a different spatial pattern. So current indicators related to NO2, such as diesel particulate matter, both diesel particulate matter and NO2 are traffic-related air pollutants. they don't have the same heterogeneities and patterns of injustice as NO2. So I'll just do a quick toggle back and forth, just so you can see the difference in the spatial pattern of NO2 versus diesel particulate matter, and see how that lines up to the percent people of color. So there is some information that we could gather from incorporating satellite data and NO2 into EJ mapping tools. So in the future, we can incorporate satellite data into EJ research and reveal new insights beyond what's available from other monitoring sources. And I've shown you some cases how disparities are stronger for nitrogen dioxide than for PM2.5, that we have larger disparities when we consider the health impacts from air pollution versus just the exposure concentrations. And we can also use satellite data to understand source contributions. So you can actually pick out individual sources in some cases, or the contribution of individual source sectors to total air pollution injustice. There's really an opportunity here to enhance information in EJ screening tools and in EJ research, and further advance knowledge and tracking by combining information from multiple sources. Imagine if you were able to combine information from satellites and from models and from monitors, you'd be able to leverage the strengths of all of these. I hope that everyone is able to engage with a new satellite data for environmental justice community of practice, because this is one area where we're learning together. This is a rapidly growing and emerging area of research, and so we really have a lot to learn from each other and from the history of environmental justice research as well. And also, I wanted to say a few words about new satellite missions that are necessary to continue the monitoring record. So I mentioned most satellites right now are polar orbiting. They orbit the planet and they take a snapshot of the Earth's air once per day in the early afternoon. NASA just launched TEMPO, which is a geostationary satellite. It will hover over the United States as the world spins and take hourly measurements during the entire daytime. And we need to be thinking about the next generation of satellites beyond TEMPO as well. NOAA is hard at work developing the next generation of an atmospheric composition satellite that they call GeoXO. And it's important for us to be supporting this satellite so that we can ensure that the satellite record continues and we have the information that we need to track and address air pollution injustice. How can satellite data be used in environmental justice applications? I challenge all of you to think about what are the environmental justice questions that you are posing in your work, whether you're in research, whether you're in practice, in policy, in action. What are the questions that you have, and how can satellite data be used to address those applications? Here I've just given a few examples, but this is really just scratching the surface. Satellite data can improve information and environmental justice mapping tools. It can be used to identify disadvantaged communities, like the way that the Climate and Economic Justice Screening Tool does for the Biden administration's Justice 40 initiative. It can be used to characterize disproportionate environmental burdens and associated health risks, and to discover associations between environmental health risk factors and health outcomes, maybe that we didn't even know before. Satellite data can be used to understand contributions of different emission sectors and sources to environmental injustice, and to identify and address local polluting sources. In some cases, you can actually use satellite data to track air pollution from emerging industries, oil and gas development, transportation related to e-commerce, warehousing, and goods movement. We can use satellite data to observe how NO2 concentrations are changing in areas where these industries are operating. And we can also use satellite data, very importantly, to evaluate emissions and concentration estimates from other sources, like from models that are used in regulatory contexts. So this is really, again, just scratching the surface. What else can you use satellite data for in your work to advance environmental justice? I've mentioned the EJ Screen tool. EJ Screen is the Environmental Protection Agency's environmental justice mapping and screening tool. It provides demographic, socioeconomic, and environmental information for any region of choice across the United States. It includes 13 environmental indicators, including air pollution indicators like PM2.5 and ozone. It has 7 socioeconomic indicators, and you can really read a lot more information about EJ Screen on EPA's website and also watch an EPA video overview. If you'd like more information and think about this question further about how satellite data and nitrogen dioxide can add value to these EJ mapping tools, I suggest looking at EPA's EJ Screen tool and map particulate matter in your area. Find particulate matter or PM 2.5. So this is a map of PM 2.5 in Prince George's County, Maryland, where NASA Goddard Space Flight Center is located. And you can see quite a bit of heterogeneity in PM 2.5. Just go to this website, load up PM 2.5 in your area, and think about what are some strengths and weaknesses of the tool and the data it uses to characterize PM 2.5? And how might satellite data provide additional information about air pollution and justice? It's not a required homework exercise, but just if you'd like more information, I think it's a useful approach to thinking about how satellite data can advance your work and your understanding of air pollution and justice. In part 3, we'll learn how to incorporate satellite-derived air pollution datasets into EJ Screen.
Thank you, Susan. Before closing out today's training, I'd like to briefly summarize some key points. Today, we've seen many examples of how satellite data have been used to investigate issues of environmental justice across a wide range of topics, including exposure to air pollution, access to green space, exposure to extreme temperatures, either heat or cold, access to water or susceptibility to droughts, and exposure to nighttime light pollution. Hopefully, this has given you an idea of the diversity of potential applications of satellite data in identifying and addressing environmental justice issues. In general, by combining different satellite datasets and appropriate socioeconomic information, we can identify potential disparities in exposure to various environmental hazards based on social and economic categories. The wide spatial coverage and long temporal records possible with satellite data allow for identifying and tracking differences in these exposures across different areas and through time, including assessing the impacts of policies meant to address these disparities. Finally, it's important to consider the spatial and temporal resolution and the coverage of different satellite datasets in order to make sure that these data are suitable for answering different types of environmental justice questions. Looking forward to part 2 of this training, which will take place in the same time next week, we'll be taking a more in-depth look at the remote sensing of air quality. Specifically, we'll cover how different types of satellites make different kinds of observations relevant to air quality. Go into some more detail about the strengths and limitations of using satellites for air quality assessment, which we introduced briefly today. We'll also talk about how what satellites measure relates to the air quality which people are exposed to at the Earth's surface. Give an overview of the current and upcoming NASA missions, which are most relevant to air quality. And finally, walk through some of the free online NASA resources which exist to help you find, access, download, and analyze different types of remote sensing data, which could be relevant to your air quality and environmental justice work. Between now and then, we'd like to encourage attendees to sign up for the NASA Health and Air Quality Community Forum, which is shown on the slide here. This is a community forum where people working on the use of satellite data for health and air quality applications can share their ideas and ask experts, including HeyCast members, for help. We've created a topic on this forum specifically related to the use of satellite data for environmental justice, as well as a subtopic specific to this training. Inside that topic, one of our trainers, Carl Mailings, who will present next week, has started a thread for participants of the training to introduce themselves and connect with each other. If you want, feel free to introduce yourselves there, including your affiliation and why you're interested in using satellite data to look at environmental justice issues. We'd be happy to hear from you and learn what you're working on and We hope that this forum will help you connect with others working on similar topics so you can collaborate in the future. I want to emphasize, though, that signing up for the HAYCAST forum is purely optional. It is not tied to the required homework needed to get a certificate for participating in this course. That homework assignment will be posted to the training webpage on the day of the final part of the training, September 6th, and will be due 2 weeks later on September 20th. To get a certificate of completion for this course, you need to attend all 3 webinars and complete the homework assignment before the deadline. If you do that, you will receive a certificate via email about 2 months later. This slide contains contact information for our trainers, as well as a link to the RSED website. You'll be able to find this slide as well as every other slide on our training website following today's training. We've also included some additional resources on this slide that you might find useful. And now this brings us to the Q&A portion of our training today. If you haven't entered your question already, please feel free to enter your questions into the Q&A box. We'll address them in the order we received them. And just a reminder, whether we get to your question or not, the Q&A transcript will be posted to the training page following the training. Okay, so we're going to take these questions one by one. We've got a number of our guest presenters here. I will kind of go through the questions, read them out loud. Please feel free to interrupt me, add any additional thoughts. If you've been the one to write the answer to the question, please feel free to unmute and speak to it. Our audience would probably love to hear from you. So the first question, are there more opportunities to join environmental justice activities via the NASA Finest proposal call? Absolutely, the Finest proposal call is issued every year. I will point out that it is divided between not just earth science, but also astrophysics, heliophysics, planetary science, and biological and physical sciences. And if you'd like to read more about it, you can access all the information through the NASA Inspire site. We've included the link there. Question 2, how are the poorly data covered regions analyzed? What is the resolution of the data? We've covered a lot of data over the course of today's presentation. In general, regions that are poorly covered by traditional ground monitors can be analyzed using direct or indirect satellite data at different resolutions. We've covered observations that have resolution as high as 1 kilometer, all the way up to tens of kilometers. In the case of sensors like Trobomi, those are going to have spatial resolutions of 3.5 by 5, it says 5.2, but I think it's 5.5 kilometers. There are also developed data sets such as surface NO2 or surface PM 2.5 that go as high as 1 kilometer. Let's see. Okay, it looks like we've discussed a number of other satellite observations in this answer, including Landsat, which has much finer resolution on the order of 80 meters and 30 meters, as well as MODIS, Aqua, and Terra. Do any of the guest presenters want to weigh in on this question before we move on to the next one? Okay, we'll go on to the next question. Where can I find data on light at night? So there is a website describing the data at NASA Earth Data. There's what's called a backgrounder, which gives information about the data itself and how to download it. And we have also actually had an RSET training on accessing the light at night, the black marble night lights data. And we've included the link here, and we can put that in the chat, I believe. What is the size of the sample population from which these associations were derived? And this is referring to the light at night presentation. I don't believe we have Xiao on the line, so we can follow up with her about this specific question, unless one of our other guest presenters might know. Okay, we will follow up with her to get an answer for this. And it looks like the next two questions are referencing her presentation specifically. Economic literature points to a positive relationship between economic development and nighttime lights. Do you think this might also explain the results? Okay, we will follow up with her. So let's go to question 7. Which satellites measure PM2.5? Will there be access to high resolution PM2.5 data set for Africa? Satellites do not measure PM2.5 directly. Satellites measure a quantity called aerosol optical depth, which is a unitless quantity measuring the amount or the optical thickness of the aerosols throughout the atmosphere. Through the use of other analysis techniques, surface PM2.5 can derive. An example of a data set derived is given here by the Atmospheric Composition Analysis Group at Washington University. If you go to this website here, there's a description of, they have global data sets available at 1 kilometer squared resolution. And those are developed using a combination of 3-dimensional atmospheric chemistry models as ground observations and many satellite observations of aerosol optical depth. And I believe that is global, so it should cover Africa. Question 8, a broad question for all of the presenters. Can you explain more about your decision on choosing the particular satellite data or product that you ended up using? Pros and cons versus other data sets, and a secondary thought that nobody seems to be using geostationary. Love to open it up to some of our guest presenters. If you'd like to speak to why you chose a particular satellite data set over another.
Hello, this is Ufoma. I can share more broadly. This isn't necessarily specific to the study that I presented about air pollution, but more broadly, choosing a product is going to be based off of what question you want to answer. As we highlighted, throughout the presentation, some of the biggest advantages of satellite data are the spatial coverage as well as the temporal coverage. And so often you might be choosing a data set because it covers a particular region or because of the temporal archive that it offers to answer a question that you might have, such as something about a time series analysis. So those are generally some of the things that go into choosing one data set over another. For example, Landsat orbits or has data anywhere between 8 and 16 days for different regions of the world, whereas MODIS has daily data. And so if your research question is something that needs to be looked at on a daily resolution, then you can't use Landsat.
Thanks. And we're going to be talking a little bit more specifics in the context of air quality observations in part 2 of this training in 1 week. Okay, question 9. Equity and environmental justice are often associated with race or the poor. However, many households are asset limited, income constrained, employed. Alice. They are above poverty level but struggle to pay the bills. These are the working poor. Is anyone looking at environmental justice issues for Alice populations? Would any of our panelists like to weigh in on any studies they might know or maybe they not know potentially Tanya or Foma.
Sorry, this is question 9.
Mm-hmm.
I'm not sure. I mean, so oftentimes analyses will usually like stratify the results by different groups. So you can see the results for not just the bottom, bottom portion of an income group or a different type of characteristic, but you can also see the results for the folks in the middle. So some analyses will stratify for different ranges of groups, and that can be seen. But in publications, I guess, yeah, people tend to focus on emphasizing the extremes.
Mm-hmm.
Yeah, I can add on a little bit here. This is Daniel speaking. In the work that we're doing, we're looking at the income piece of this because that's helping us hopefully to infer something about energy insecurity. That is, if people are differentially rationing their energy use in relation to their income. The question, I think, is really important because it speaks to this asset question, which is essentially a measure of wealth. And it is something that has been studied in the United States, that some of that wealth disparities are some of the most important potentially to be thinking about with regard to health. The problem there is that we don't have as many great measures of wealth nationally as we do for things like income. And so it's a piece that I think if we had better data that we could marry with these satellite measurements, that would be an important direction potentially for some future work here.
Great, thank you.
Hi, I can also add on that besides income or poverty or low socioeconomic status, some of the studies we reviewed also use social data sets like subsidized housing or students who are qualifying for school meals, and then of course Medicaid recipients, which could cover a wide range, although all low income, but a range of incomes. This is Tanya. Thank you.
Great, thank you. So it sounds like there's a wealth of socioeconomic information to compare against, and we can look for potentially specifics about the listed qualifications shown here. Going on to the next question. Light at night may not be considered a factor in the Nigerian context due to poor power supply at night. However, could there be any environmental justice due to lack of light at night? Which is a really interesting question. I am not aware of any studies, but absolutely, I'm assuming lack of access to electricity could be investigated using that data. No lights at night have been used to analyze lack of electricity following disasters as well. Question 11 is asking for the full citation by Dr. Carrion, and it is listed here. Question 12, how could this data gap improve in an investigation where I use satellite images and due to cloud cover in mountainous areas, I have very few valid satellite data, for instance, AOD. Absolutely, clouds are absolutely a limitation of satellite data. Often by spatial or temporal averaging, we can overcome the lack of clouds. Also using geostationary data or incorporating three-dimensional chemical model output can be ways to overcome. But indeed, that is a barrier, and usually people use averaging to try to get a signal. What are some examples, question 13, what are some examples of reflective surfaces that might interfere with satellite data? Examples are water, snow, ice, sandy deserts. These in urban areas, metal and glass, these can interfere with the retrieval algorithms that are used to derive the variables in question. Question 14, can we quantify air pollutants using satellites? Yes, we can. Certain pollutants can be identified using satellite data. We've discussed a number here. We'll go into more detail next week, but we should emphasize that a satellite is seeing the entire atmospheric column, and more information is typically needed to infer a surface concentration, which is typically the most relevant for environmental justice or air quality applications. Can you share whether there is any NASA data available on methane and any associated mapping efforts? Yes, there's definitely several NASA missions that measure methane. It looks like we've included a link here, and we'll touch on this briefly next week. Question 16, are there any specific challenges in using satellite data for air quality monitoring in urban areas as compared to rural areas? Absolutely, high variability in land surface cover and reflectivity in urban areas compared to rural areas. We'll be discussing some of this next week. And it looks like either Tanya or Ufoma has added. Feel free to unmute.
Yes, hi, this is Tanya. In our scoping review, we found it interesting that when researchers analyzed urban or rural areas, it was not always consistent, although most researchers did find that highly dense urban areas had higher exposure to environmental hazards such as urban heat or air pollution. But the example that I gave here was showing that one set of researchers found more nitrogen dioxide exposure in urban areas rather than in rural areas, which would follow the reasoning I just gave. But another set of researchers actually found more of an association between PM 2.5 exposure and mortality among elderly populations in North Carolina and Michigan that were actually higher in the rural areas compared to urban areas.
That's very interesting, and might speak to a little bit of what Susan touched on with the spatial, the high gradients seen in something like NO2 versus the more regional PM 2.5 spatial variability. Thank you. All right, we're already over time. We'll take another question or two. Is Tropomi open access, and can one see levels from South America? Yes, all Tropomi data are open access and can be accessed through NASA's data portals. We'll talk about this more next week. And it is a polar orbiting satellite, which means it sees the entire globe once per day. Because of the swath, I should say, there's daily coverage. Question 18, how are the figures in the presentation made? It looks like several of the graphs in Susan's were made using Python, but you can also use other programming languages such as R or MATLAB or GIS software or Google Earth Engine. We'll be showing an example using Python in part 3 of this training series. Question 19. Do you have examples of how this information has affected policy decisions? I would invite one of our guest speakers to speak to this one.
Yeah, I can talk about this one. I really think that we're just at the beginning of seeing satellite data being applied in policy contexts. So the examples will continue to build, hopefully through all the great work that you all on this training will go forward and do. But one example is a municipal government in the United States who used satellite-derived air pollution estimates and the associated health risks to determine where to deploy electric buses instead in the lieu of the dirty diesel buses that were driving around the city. And the aim they had was improving air quality for overburdened communities. And another example is the U.S. Environmental Protection Agency, who's already using satellite data in their air trends report, just to show how nitrogen dioxide has changed over time as a result of our regulations here in the United States, and also to assess exposure and risk as part of the National Ambient Air Quality Standard setting process. But I really encourage everybody, if you have other examples, consider posting them in this community forum. Because this is the idea of building a community around satellite data for environmental justice. We can share lessons learned from our own experiences, the challenges and opportunities, so that we can really pave the way for others to use satellite data to advance environmental protections.
Hi, this is Tanya. Since we looked at 81 studies, we also found a lot of different examples where sometimes researchers touched on policy implications or public health and agency implications, but a lot of them did not give very specific examples or community level impact examples that we were interested in. But some did, and I can go over just a couple of the examples that we did find very interesting. One of them, my colleague Ufoma already touched on with the City of Detroit planning in the presentation that you've already seen. But another example we didn't go over there was Kondo et al., which did a study on Philadelphia, and they were looking at their city planning for the future, a 30-year plan. And they did find that if they increased the urban tree canopy by 30%, they found that there would be less mortality from air pollution and air pollution-related illnesses. And those areas that would be affected would be those of lower socioeconomic status, including African Americans. The policy implications that we were really looking at too were for urban planning, even for community planning, for interventions that can take place at the ground level, especially land use planning. And we find that the communities, now that there are more user-friendly applications of satellite data, community organizations and nonprofits could eventually be linking with public health departments or with policy level actors to use satellite data more to be able to actually go out to the sites which are found to have more environmental hazards and try to mitigate them. For example, by putting more ground monitoring, if that is necessary for air pollution monitoring and air quality, or by planting more trees of different species. Another article, this will be my last example, was that one of the studies specifically looked at the Clean Air Quality Act, and they showed that even though air quality has improved over time, there was a definite increase in some communities of having higher disparities. So the satellite data can be used as an objective evidence. It's important that different actors at community levels and public health levels and academia and science teams come together to encourage agents and agencies like the Environmental Protection Agency to use more satellite data in their screening tools or to advance public health efforts which incorporate some level of satellite data, always combined, of course, with socioeconomic and demographic data in order to have an environmental justice impact. Thank you.
Thank you. I think we'll end it there for today. We're already 13 minutes over our scheduled time. Before we conclude, just want to open up any final words from our guest speakers. Just wanted to offer you the opportunity. Okay, if not, I will thank everyone so much for their amazing presentations. Thank you so much for your valuable contributions to this training. Please join us next week where we will take a deeper dive into satellite observations relevant for air quality. Thank you to the behind the scenes RSET team, Brock Blevins, Natasha Johnson-Griffin, Selwyn Hudson-O'Doy, Carl Mailings, Sarah Strode, and Sarah Cutchell for their assistance with this training, and we hope to see you next week. Thank you again for joining us today.